So in this lecture, I'm going to start comparing gravity to electric forces. We haven't talked much about electric forces, and honestly, it's a very small component of this class. Mostly, you're going to cover things in great detail next semester in Physics 152. But it's important to look at the similarities and the differences as we go forward. So one thing I'd like to introduce before we get too far is the notion of reciprocity. And it's just a way of saying equal and opposite. And so, for example, if we look at a similar problem compared to the one that we did in class, where I take the sun, for example, and the earth, or any planet and any star, or any gravitationally attracted bodies, the force on the sun by the earth will be equal in magnitude as the force on the earth by the sun. However, they will point in opposite directions. These are attractive forces, and so I can write down that this is a true statement. These are forces due to gravity. And so all force pairs in this situation, where we have one body acting on another body, and vice versa, that body acting on the other body, will have a pair of force vectors which will be equal in magnitude, and in the case of gravitation, will be the opposite direction. So I have to put a minus sign. And this is also the third law of Newton. It's another way of saying reciprocity. Reactions come in equal and opposite pairs. Okay? All right, so that's the idea of reciprocity. That also applies to electric forces. And so the electric force is the force felt between fundamental particles, such as, in this case, I've labeled them in different colors. We might have a positive charged particle. This might be a proton, for example, what you find in the nucleus. And we may have a negatively charged particle. This might be an electron. There is a zoo of different particles available, and all of them have some magnitude of charge. The fundamental charge is that of the electron, minus E, is what we call that. And it's equal in magnitude to the charge of the proton. Now, if I take two protons and I put them near each other, they will experience a force to push them apart. So these forces are positive, and they are directed along the line that connects the centers and are set up to push the particles apart if their signs are the same. If their signs are the same but of the different value, the minus charge, you also get that the force along the centers is one that will tend to push the particles apart. However, if I have a sign minus and a sign plus particle of equal magnitude in charge, the amount of charge, this also has charge E minus. I'll take the magnitude. So it's like this. Then they will tend to attract. This is much like a gravitational force. So to write down the value of the electric force, force electric, I have to keep track of not only the sign of my charge, but also what the force loss should look like. And remarkably, it is a vector force, so there has to be some vector component, so I'm going to call that r hat. R is the distance from one charge to the other, and r hat, of course, is the direction vector that points in that direction. And so there's a constant called K. This is the electric constant. And there are two things that we have to consider. One is the charge of particle 1 and its sign, and the charge on particle 2 and its sign. Additionally, we have to always consider the distance that they are separated, and that distance squared will give the proper force relationship between these two charged particles. So let's walk through this. You see the similarities with gravity, I hope. And we have a force law dependence that goes vectorially along the sign, or along the direction of the line connecting the vectors, and the magnitude of that force will be proportional to 1 over the distance between them squared, so r squared, r magnitude squared. Okay, this is a constant. Charges come in magnitudes, and so for example, I'm going to give you the value here of K. K is equal to 1 over 4 pi epsilon naught. Those are just numbers. And it's equal to 9 times 10 to the 9 Newton meter squared per coulomb squared. Coulombs are the fundamental unit of charge, 1 coulomb. And the charge of an electron is equal to minus the charge of a proton, and that's equal to 1.6 times 10 to the minus 19 coulomb. Okay, so those are our units. Now, if I look, for example, at two positive charges, I'm going to get q squared, but it's going to be a positive sign. So a positive sign means that the force on this charge, due to this charge, will be along the direction of the vector that points between their centers, so it pushes that way. And if I flip it and say, what's the force on this charge due to this charge? Well, then I have to take into account the vector that points along their centers from this charge to this charge, and it will point in the same direction as that connecting vector. And so every time I take into consideration a different charge, I have to take into account the direction of the vector that points from the charge that's acting on the charge I'm interested in. And so I always flip my r vector if I flip my index. For example, if I call this charge 1 and charge 2, if I want the force on 1 by 2, or the force on 2 by 1, I have to flip my vector to recognize that this is the vector 2, 1. Or, if I turn it around, this will be the vector r 1, 2. So you have to be consistent with your vectors so that you get your force directions right. In this case, it's very similar to gravity. Again, this is r pointing to 1. And so force here will have the product of these two charges and their signs. So I pick up a minus sign. And so now the force goes against r hat. It's the other direction. It comes inward. Minus forces, vector forces that are negative, are attractive forces. That is something to remember. Remarkably, this r squared is exactly like gravity. Okay, so what I'd like to do now is do a quick example to show you the difference between the gravitational interaction and the electric force interaction between, for example, two protons. Here's a proton and a proton. These will repel each other due to their electric force, but they will also attract each other due to their gravitational force. And we're going to compare those two things. And here I've taken another situation where I've taken the Earth and the Moon, I've separated them by their nominal distance, but I've put a tremendous amount of charge on each one of these. In the universe, most things are charge neutral. We don't have to worry about a lot of excess charge floating around. And in fact, this is a tremendous amount of excess charge. If I had the Earth and, for example, a building that had these two disparate numbers of coulombs acting on them, I would be able to launch that building to outer space at rates of accelerations that you would not believe. So this is a tremendous amount of actual charge. It's a lot. So that's not really realistic, but it is something we can make a comparison now between the gravitational and the electric charges in these two scenarios. Okay, so let's go ahead and do that. So first I'm going to take a look at the force due to the electric field or the electric charge. And I'm going to work in magnitudes here, so I'm going to drop most of my values for the vector quantities. So I'll just say K, this is a Q plus and a Q plus divided by, of course, the distance that separates them. And I'm not going to put the vectors here, I'm just going to now just work completely with scalars. So we can look at the values. So we have 9 times 10 to the 9 newtons meter squared per coulomb squared times, well, this is the charge, the fundamental charge, 1.6 times 10 to the minus 19 coulombs, divided by, and I'm just going to leave this r squared because eventually we're going to take a ratio and the r's are going to go away. So the force due to the gravitational interaction, well, it's g, the mass of the proton, over this r squared. And so g, as we know, is 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. And this will be times, well, it's the mass of the proton squared. The mass of a proton is 1.7 times 10 to the minus 27 kilograms, quantity squared, divided by, of course, r squared again. Now, if I take the ratio of the electric force to that of the gravitational force, well, I have this on top and this below. The r's go away, and what I'm comparing is 9 times 10 to the 9 times 2.6 times 10 to the minus 38, okay, over 6.7 times 10 to the minus 11 times 2.9 times 10 to the minus 54. That's an enormous number on the bottom. And what that gives me in the end is 1.2 times 10 to the 36. So what that means is that the electric force is 36 orders of magnitude more powerful than the gravitational force. So if I were to put these electric charges at this distance, a nominally corresponding distance, the effect of gravity is 36 orders of magnitude less than the effect of the charge. That's remarkable. So I'm going to say F electric to F gravity is approximately 10 to the 36. Okay, so let's keep that in mind. And let's switch gears and go to the other example which is gravitation. Okay, so let's do that. We've got two masses to worry about. We've got the mass of the Earth and the mass of the Moon. Those are going to be equal to 6 times 10 to the 24 kilograms and 7 times 10 to the 22 kilograms, respectively. So let's look at the charge that we have and the electric force, F electric. Now this is with the Earth and the Moon. And so I've placed an amount of charge on here. So this is going to be 9 times 10 to the 9 Newton meter squared per kilogram squared times 10 Coulomb squared over R squared. Okay? Now, oh my goodness, it's Coulomb squared. This is now going to be F gravity. Okay, so we have 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared times, well, 6 times 10 to the 24 kilograms times 7 times 10 to the 22 kilograms divided by R squared. And now if I take the ratio of those two values, F of gravity, I'm going to do this, F of gravity over F electric now. Well, that's going to be equal to 6.7 times 10 to the minus 11 times 4.2 times 10 to the 47 divided by 9 times 10 to the 9 times 100. And that is equal to 3.1 times 10 to the 25. And so what you can see now is that when I change my perspective, I think now about the amount of gravitational interaction with these two massive bodies. They're massive. They weigh, their mass is a lot by comparison. Gravity dictates in the case where you have a large amount of mass. We saw that the amount of electric charge on each one of these was really quite small, 10 to the minus 19 coulombs. This is 20 orders of magnitude more charge than this. But in the case where you have large masses, gravity is the dominant feature. Here I can say F due to gravity over F due to the electric charge is now 10 to the 25 in terms of that ratio. So force due to gravity is 25 orders of magnitude stronger when I have large masses separated by large distances. When I have small masses separated by nominally small distances with charge, the electric force is the dominant force. Okay, so something to keep in mind.